Today's lesson is a continuation of section 11.4, apply the Pythagorean theorem and its converse. Today I'll talk more about that second part, the converse of the Pythagorean theorem. That's another way we can use this formula to help us answer some questions or answer some problems that we may see. First of all, just a review of the Pythagorean theorem. Or what is it? Well, it comes down to really this formula. A squared plus B squared equals C squared, and it applies for just right triangles. This is the relationship that holds true for all right triangles, no matter what the side lengths are. A squared plus B squared, if I add these two together, I'm always going to get whatever C squared is. And so any right triangle, if I know two of the sides, I can always find the third side, no matter what combination, whether it's A and C or A and B or C and B, it doesn't matter. Just some key terms that we used for the right triangle also, that the hypotenuse, that stands for the side opposite the right angle. So here's my right angle. There's C. That usually termed as C for a variable, but that's always the side opposite the right angle. That has to be the longest side in the right triangle. So, and that has to go in for the variable C when we're talking about the formula. So the hypotenuse is always C. A and B are just the other two legs of the triangle. Usually doesn't matter what order they're in, but those are two words we might also use, hypotenuse or legs, the two other legs for the right triangle. When we say those words, that's what we're talking about in terms of where the numbers may go in for the formula. A squared plus B squared equals C squared. Well, in the previous lesson, I showed you one way we can use the Pythagorean theorem. Like I mentioned, is if I have two sides, I can always find the third side of a right triangle. Another way we can use it is to actually define what kind of triangle we have if we're given three sides, knowing that they're going to make a triangle. So they might get a problem that says something like, do these sides form a right triangle? And they give me sides 9, 12, and 15 for A, B, and C. So if I had three sticks that were each that length, like 9 feet, 12 feet, 15 feet, or whatever the units is, could I make a right triangle? Would these three sides form a right triangle? And either they will or they'll form some other type. No matter how I arrange them, either it will make a right triangle or it'll make some other type, which I'll talk about here in a second. Just using these numbers, though, and the formula, I can tell you. I don't even have to have the actual props with me. I could just figure it out. What I do is I just like the formula says here, I'm just going to plug in 9 for A, 12 for B, and 15 for C. And as long as, and when I'm checking for this, checking to see if it's a triangle or not, or what type of triangle I have, it needs to be that the longest side has to be C. Because again, that would be the hypotenuse if this were even possible, if this even works. So make sure whenever I'm checking something like this, the longest side definitely needs to be plugged in for C. So what I'll do is I'll plug in 9 for A, so I'll have 9 squared plus 12 for B, so 12 squared equals 15 squared. And it's kind of like a question mark here I'm seeing, does this work? Is 9 squared plus 12 squared, does that equal 15 squared? Well, 9 squared is 81, 12 squared is 144, and 15 squared is 225. And if I add 81 and 144, I think I do get 225. So yeah, those numbers do work in the Pythagorean theorem. I get the same thing on the right side as I do the left side, so this must be a right triangle. Gotta get some angle, there we go. That must be a right triangle. Well, this is essentially, that example is showing the converse of the Pythagorean theorem. Pythagorean theorem said if I have a right triangle, then this formula works. Well, the converse would say then, if that formula works for three numbers, you must have a right triangle. So that's what the converse of the Pythagorean theorem is. Just kind of, converse means just kind of, for a theorem, it means you just kind of reverse the order of the hypothesis and the conclusion. You just say, okay, well, yesterday we said if we have a right triangle, then A squared plus B squared equals C squared. That formula has to work. Well, today we're saying if that formula works, then that triangle has to be a right triangle, which is exactly what it says here in the book, or as I've got up here on this page. Well, so we know that if we have a right triangle, if that formula works, we have a right triangle, which again looks like this. I have A, B, and C. And what do we know about a right triangle? All right, a right triangle has one 90-degree angle. So I know that about right triangles. Well, what if the formula doesn't work? What if I plug in three numbers and I don't get something that's the same on the right side as I do the left side? Well, then I must have some other type of triangle, or something else must be happening. We have to think of the other triangles that we know that are defined by angle. Right triangles are defined by the fact that they have one right angle. What other triangles do we know that are defined by angle, like how big or small they are? Well, one of those cases is the obtuse triangle. And usually I'll ask students to remember these in class, and they usually be able to come up with these. The obtuse triangle, what does that look like? Well, it has one angle that's actually greater than 90 degrees. So here's an obtuse triangle. And this angle right here is actually going to be greater than 90 degrees, greater than just like the corner of your paper. So that's what I know about obtuse triangle. Has one angle that is greater than 90 degrees. There's the greater than sign. Greater than 90 degrees. So I know that about obtuse triangles. And then one other type of triangle that's defined by angle is the acute triangle. Oops, and not AU, but AC. Acute triangle. What does an acute triangle look like? Well, it actually has no angles that are greater than 90 degrees. So then it wouldn't be possible. None of them can even be. It's not just that one of them is less than 90 degrees. It's the fact that all of them are less than 90 degrees. So for an acute triangle, all angles are less. I'll use the less than sign again. Less than 90 degrees. So here are the three types of triangles that are defined by what their angles are. Using the Pythagorean theorem, or I should say the converse of the Pythagorean theorem, and using that formula, a squared plus b squared equals c squared, if a problem gives me three sides in a triangle, and I plug in the numbers, and no matter what I get, I can tell which type of triangle I've got without even trying to construct it. And I'll show you how we can do that. So at the top there, I've still got the converse of the Pythagorean theorem. And just like I've been asking here recently, what if a triangle is not a right triangle? Can we tell what kind of triangle it is by using the Pythagorean theorem? Well, yes, we can. First, I'll show you this first example here, though, which will show you again what happens when the formula works. What if they give me a problem that says, tell whether this triangle is an acute, obtuse, or right triangle by using the Pythagorean theorem? And they give me the three sides that would form this triangle. Well, if I have a 6, 8, 10 triangle, just remember that for a couple of the numbers, it doesn't really matter where they go, but the biggest number definitely has to go in for C. Okay, for this to work at all, the biggest number has to be the hypotenuse. So 10 has to go in for C. 6 and 8 are A and B in this case. Well, 6 squared plus 8 squared then's got to equal 10 squared. And I'm going to check and see, question mark, does this work? 6 squared is 36. 8 squared is 64. 10 squared is 100. 36 plus 64, what does that give me? I think 36 plus 64 is 100. So yeah, 100, well, that equals 100. They get the same thing on both sides of the equation. So this must be the right triangle. Showing a picture of what this might look like. Here's a right triangle. Here's 6. Here's 8. Here's 10. So there's my sides. There's what it looks like when the converse of the Pythagorean theorem works. When I plug the three sides in, and I get the same thing on both sides. That means it must be a right triangle. Well, what I was telling you earlier, though, is that we can also tell what if the numbers don't work? What if I don't get the same thing on the left and right side? Then I must have one of those other two cases where either I've got an obtuse triangle because it's not a right angle, it's too big to be a right angle, my biggest angle, or the biggest angle is less than 90 degrees and I have an acute triangle. So it must be one of those two cases. Well, here's how we can find out using the numbers. Look at this problem right here. Now I have 6, 8, 13 for my dimensions. So almost the same as the last problem, but this last number is a little bigger. Usually at this point in the class, I'll ask people if they can maybe even figure it out before I even do this problem what type of triangle this might be. And some students are able to, but I'll show you with the numbers here first what happens. So let's say it's the first problem, number 1. I had 6, 8, and 10 as my three side lengths. Well, this one I have 6, 8, and 13, so pretty similar, but that last side's bigger. So maybe even in your head right now, you start thinking, what case do you think this might be if the longest side is longer than it should be, okay, to make a right triangle? Well, if I put the numbers in though, like I was doing, 6, 8, 6 squared plus 8 squared, and then again 13 squared has to be C because that's the biggest side. So equals 13 squared. 6 squared gives me 36. 8 squared gives me 64. 13 squared is 169. If I add 36 and 64 again, I still get 100, but that's less than 169. So realize what happened here. This biggest side, like I showed you, compared to the first problem, is bigger than what the side was in the first one, right? Go to the triangle and think about what this would mean. Let's say this longest side wasn't 10 inches, but instead 3 more inches extended. So let's say it's 3 more inches out here. And then this one will still say is, let's say it's close to 6, and this one's about 8. Well, what happens in this kind of triangle is that the C side, what could be the hypotenuse, but it's not a right triangle, so it's not, but what could be the hypotenuse is too long. The C side is too long compared to the other two sides to form a right triangle, so that makes it an obtuse triangle, as you can see here. It extends that angle out. So this is what happens when you end up getting this case where A and B added together, which was 100, is less than what C was squared. This is when you get the obtuse case. And you can kind of see it again from the picture, thinking about, okay, the C squared, this ends up being bigger than the other side, because the C squared, that longest side, was too long. When I squared it, it was longer than, or it was a bigger number than the other two added together. So if C squared is bigger than the other two, that's when I get the obtuse case. Okay. Well, now example number 3 then. Of course, I have one of each case up here. What's going to happen in this one? This one I have 6, 8, and 9. So this side's a little smaller than the other ones, right? I'll show this one on the picture first. As opposed to having a side of 9 or side of 10 for this one. Now if I have a side of 9, that means it would stop maybe somewhere around here. And then let's say this is still about 6 and this is still about 8. Well, what happens is that longest side, the C side here, what could be the hypotenuse, but it's not because it's not a right triangle, but this longest side ends up only being 9 inches long. Well, then it's too short to make a right triangle. So as you can kind of see already from what happens here, why I get a triangle that shrinks this angle down, ends up being less than 90 degrees. And so now I should get the acute triangle case. Looking at what happens with the numbers here. 6 squared plus 8 squared equals, well, 9 squared. We're checking to see if that works. 6 squared is 36. 8 squared is 64. 9 squared is 81. If I add these two on the left side together, I get 100, which is bigger than 81. Oops, 81. So again, in this case, when A and B squared and added together is bigger than what C is, this is when I get the acute triangle case. I've showed it in those 3 examples, what happens for each case. Here's kind of the straightforward what to write down in your notes in case you're, again, somebody who likes it. Well, exactly what do I do, Mr. Cato? What happens? Well, here's those lines that might help you with that. How to tell what kind of triangle you have. If you plug the 3 numbers into the formula and it works, they're equal, then you must have a right triangle. If you plug them into the formula and you end up getting that C squared, that side is bigger than the other two added together, well, what that means is, again, this C, whatever that longest side was too long to form a right triangle. And that stretched the triangle out and made an obtuse angle for that biggest angle, so now it's an obtuse triangle. Or if you plug the numbers into the formula and A and B squared is bigger than what C squared is, then the two A and B sides, those are longer, C is shorter, and so it doesn't form a right angle, it's something short of a right angle, so that makes it an acute triangle. Those are the 3 cases we'll run into when we're talking about the converse of the Pythagorean theorem. If they're having us check 3 sides to see what kind of triangle we got, it's going to be one of these 3 cases. So going through one more set of examples here just so we can kind of see it one more time and see how it works with the numbers. So if they ask me what type of triangle do I have here, I've got sides 12, 18, and 25. What I'm going to do is just plug those into the Pythagorean theorem here, or to the formula. And again, the longest side, this definitely has to be C because it's the longest side. I've kind of set them up nice in the examples here. But whenever you're doing these problems, make sure you check and see which is the longest side and put that in for C. 12 squared plus 18 squared. Does that equal 25 squared? We're going to check. 12 squared is 144. 18 squared is 324. 25 squared is 625. Adding these ones on the left side together, what do I end up getting? Well, again, let's see, 8, 4, 6, 4. I get 468, which is less than 625. So again, this c squared, this c by itself squared was bigger than the other two. So if that's greater, that's when I get the obtuse case. Again, what you can think is this longest side is longer than it needs to be. And so then it created an obtuse triangle when I tried to line the sides up. It stretched out this angle, it made it a larger angle than it needs to be. So it can't make a right triangle, it's an obtuse triangle. The second example, 5, 12, 13. 5 squared plus 12 squared equals 13 squared. I just plug them in the formula. I'm going to check. Is that true? Question mark. Is that true? Is 5 squared plus 12 squared equal to 13 squared? 5 squared is 25. 12 squared is 144. 13 squared is 169. Add these two together, I think I get 169. So I get the same thing on both sides. The Pythagorean theorem worked, or that formula for these numbers, so it's got to be a right triangle. These must be sides that I can line up to form a right triangle. And then this last one, same thing. I'm going to check 19 squared plus 23 squared. Is that equal? Question mark. Is that equal to 27 squared? 19 squared is 361. 23 squared is 529. And I think 27 squared is 729. Yep, it is. So I'm just going to plug the numbers in the formula, square each one. When I add these two together, what do I get? Well, I get, let's see, 0, bring up the 1. I get 9, 8. So 890, well, that's bigger than 729. If A and B squared, if these two added together are bigger than C, this must be the acute case. The C squared, that longest side, isn't long enough to make a right angle. I can just kind of show on the picture what would happen. It might happen like where it stops about right here. The C squared side isn't long enough, so now I get a smaller than 90-degree angle here, and I get the acute triangle case. Those are the three cases. When it's another way to use the Pythagorean theorem, checking to see what kind of triangle you got. It'll always be one of these cases will happen when you plug those numbers in.